So let's say that we have two cars. You can pick any two of your favorite cars. We'll say that's a Ferrari and that's a Lamborghini. So in the first situation, the car has a zero velocity, so it's at rest. It's not moving at all. In the second one, the car is moving to the left with a velocity v. So if we look at the problem, it says that these cars contain a buzzer, and the buzzer is emitting sound waves at a certain frequency. So just to visualize it, we'll do it for this one. So the buzzer will emit sound waves, uh, something like that, and it'll hit the microphone, and the microphone will pick up some frequency. We'll just call it frequency sub x. So just as a precursor, we're not given any numbers in this problem, so this is purely conceptual. In the second one, the car is moving to the left with a velocity v. And so what we see is that this is going to be a Doppler effect problem. And what the Doppler effect essentially says is that as a car or any object is moving towards you, the waves are going to become more compressed, squished together. And as an object is moving away from you, the waves will be more stretched out. So if just to the side we draw a visualization of what that is, so let's say that normally it'll be something like this. So we'll have waves coming off of it. They're all supposed to be the same distance, but I just can't draw. But what we see is that if this object is moving to the left at velocity v, what's going to happen is that this microphone is going to see the objects as more, as the waves, sorry, as more squished, so they'll be more compressed like that. And this microphone, since the object is moving away from it, it'll be more stretched out, so something like that. So this stretched out and shrinking is simply a matter of frequency. So Doppler effect tells us about how frequency changes based on the object's motion. So what we see is that these waves, since if an observer was standing here, they would hear more waves per second because the waves are more squished together. So you experience more waves more quickly. Therefore, there's a greater frequency of the waves. And an observer standing over here would experience a lower frequency for the same reason, vice versa. So let's erase this to make some more room. And so let's go back to the problem. So in investigation 1, we already said that the microphone X is picking up some frequency, frequency X. And so in this situation, based on the Doppler effect, the physics background we just talked about, microphone Y is going to experience these waves as more squished together, so at a higher frequency. And this is why it doesn't matter what this velocity v is. All we care is that the object is moving to the left, therefore the waves are more squished and there's a higher frequency. And on this end of the spectrum, for microphone Z, the waves will be more stretched out, something like this. This is kind of dramatic, but that's essentially the point. And so now looking at the problem, it says represent the frequencies picked up by each microphone on a graph. So let's just label them, because that's always good to do. So for microphone Y, we'll just call that frequency sub Y, just because it makes sense. And then for microphone Z, frequency sub Z. And so remember, we're not given any numbers in this problem, so all we need to do is compare their relative frequencies. So if we draw a graph up here, so we'll put this side as frequency, the y-axis as frequency. We'll say in hertz, but honestly it doesn't matter because we're not given any numbers, so the units doesn't really matter, but we'll just put that. So then we have frequency, and then we'll just say this is time in seconds, just arbitrarily. So we know that the frequency is going to stay constant because, well, in this case, the car is just staying there. It's not changing its motion at all. There's no acceleration, so the frequency will be constant. So we'll just pick a spot. We'll say the middle, just because later it'll be easier. And we'll just draw a straight line, because the frequency will be constant over time. And let's just label this line so we know as frequency sub x. So this is in investigation 1, the frequency that microphone X will pick up. Next, in investigation 2, let's look at microphone Y, just to go down the alphabet. And so we already talked about the Doppler effect. We said that these waves will have a higher frequency. So microphone Y and f sub Y will be bigger than f sub x. So we'll draw a line above f sub x, and we'll just call it f sub y. Now, this f sub y line could be here, it could be up there, it could be off the table for all we know. It could be so much greater, but it doesn't really matter. We're just comparing it relatively. So all the question is asking us for is that is f sub y greater than f sub x or less than? And of course, there's a third variable, which is f sub z. So the frequency that microphone z will pick up. And we talked about the Doppler effect again. And we know that these waves will be more stretched out, and the frequency will be lower than what microphone x would pick up, since the object is moving away. And so we'll just draw a line here and call that frequency sub z. And yeah, that's our graph. And so next, this is a CER problem. So let's write down the steps. So first, our claim. We're essentially claiming that this graph is right. So we're claiming that graph is right, but in more formal terms, we're saying that the frequency that y will pick up is greater than the frequency that x will pick up, and this is y, that's x, which is greater than the frequency that z will pick up, which is that. And so our evidence is just going to be the Doppler effect. So if you were to explain this in a problem, you would just explain what the Doppler effect is and how it applies to this situation. So in this case, the car is moving away from this microphone and towards this one, so the waves will be stretched a certain way, as we talked about. And so that will be our evidence. And so for our reasoning, we need to find a real-world example of why this would make sense, why this physical concept actually can be applied. So, for example, if you hear an ambulance or a fire truck moving away from you, the sound, the pitch, will become lower because the frequency will drop. That's due to the Doppler effect. And if this fire truck or ambulance is moving towards you, it sounds sharper. And now, it's important to remember that this example isn't about whether the sound sounds louder or softer. That's because of amplitude. All we care about is whether the pitch is sharper. So if it's like a high C, like ah, that means that the frequency is higher. We don't care about whether it's louder or softer. So fire truck or ambulance. And if you wanted to go even further, you could talk about how when stars are moving away from us, their light is something called redshifted, which you probably hear a lot on the news. So what that essentially means is that instead of sound, as the planet or a star is moving away from you, the light waves get more stretched out and they have a lower frequency, so they go down the electromagnetic spectrum and they have a lower frequency. They'll become red. And vice versa, if they're moving towards you, they're blue shifted. They move the other way up the spectrum towards gamma rays and x-rays and all that good stuff with really, really high frequencies. So if you want, you could talk about we'll say celestial movement as another way of reasoning it. And so that's the problem.